All right, so we're going to start now with our second section on the energy and enzymes chapter, and we're going to keep getting a little more specific into energy in living systems. And so, as we talked about in the first section, most of the energy in the living world, with a few exceptions of prokaryotic things that live, deep underground or deep in the under the ocean, those kinds of places, most life on Earth exists because of the sun. Right, so sunlight comes in, autotrophs capture it, heterotrophs take advantage of some of the energy converted from the sun into the autotrophic bodies. So, one way to think about this is that in order to maintain a low entropy or high complexity state, right? So, if it's low entropy, it has to be high complexity. One way to maintain that kind of a state is to continuously add energy. And so it turns out that's actually the only way to maintain complexity and lack of entropy is by having energy coming in all the time to the living world. All right, so without energy, entropy wins. That's basically the idea we're dealing with here. So we talked about our autotrophs, we talked about our heterotrophs, consuming autotrophs or other heterotrophs. All of this is based upon the autotrophs initially storing up some of the sunlight energy in the bonds of carbohydrates, which can then be transferred into other organisms. When we look at entropy in general and how common it is in the universe, we can see things that happen more or less spontaneously, right? So if you dump salt into a glass of water, the salt's going to dissolve. If you see a bike sitting at the top of a hill, if you give it a little bit of a push, it'll roll downhill by itself. But once the salt is dissolved in the water, and once the bike is at the bottom of the hill, you're not going to see the salt come back out of the water, and you're not going to see the bike go uphill by itself. Both of those kind of oppositions to entropy require energy input. So if you want to get your salt back from the water, what do you have to do? But you got to boil the water off, and you'll eventually get your salt back. But that's energy input, right? If you want to get the bike back to the top of the hill, you have to spend some energy to get it there. It's not going to go by itself. So when we say spontaneous, these are things that happen as a result of entropy kind of winning out in the universe and complexity losing in the universe. If you want to create complexity from less complex things, you have to add energy. That's kind of the basic rule that we're dealing with here. All right, so when we talk about energy conversions taking place, anytime we convert energy from one form to another, some of the energy is going to be given off as heat. Now, it's important to remember that the energy is not lost per se. It's not lost from the universe. The energy is still there. It's just heat energy. But in terms of energy available for living organisms, once the energy is heat, it's pretty much useless as far as the living organisms go, right? So as far as the living organism is concerned, once the energy becomes heat, it might as well have been lost from the universe. Even though it's still in the universe, it's not usable by living things. So what that kind of gets us to is if we're dealing with something like a food chain, right? What happens if we're dealing with some autotrophs and then various numbers of levels of heterotrophs that kind of feed on each level that came before it? You got to start with a lot of energy to make a food chain actually exist. So what I'm going to do is kind of give you an example of what that would look like. So we're going to imagine that we start off with like 1,000 kilograms of seeds, tree seeds, whatever. 1,000 kilograms is about 2,200 pounds. So it's a little over a ton worth of seeds. So if we take those seeds and feed them to a heterotroph, like mice, for example, those 1,000 kilograms of seeds, I forgot my number for a second, the 1,000 kilograms of seeds will translate to about 100 kilograms of mouse biomass. So we're losing, quote unquote, 90% of the energy that was initially in the seeds that was made by the plant. 90% of the energy is being given off as heat, and only 10% is used to build those 100 kilograms of mouse biomass. So if we take the mouse biomass, the 100 kilograms of mouse biomass, and we feed that to the next level in the food chain, some sort of snake, for example, now we're going to be down to around 10 kilograms of snake biomass. So again, we've lost 90% of the energy that was in the level before. And again, it's not really truly lost, but it's given off as heat, so it's not readily usable by living things. And only 10% of that energy was used to be passed on to the snakes, which is actually 1/100th of the energy that was present in the seeds to begin with. So every time we convert from one level in the food chain to another, we're losing about 90% of the energy, and 10% of the energy is being carried on to build the next level in the food chain. If we were to take one more step in the food chain, and most food chains are limited to maybe 4 or at most 5 steps or 5 levels in the food chain. In this example that I'm giving you now, something that would consume the snakes would be something like a hawk, for example. If you have 10 kilograms of snake biomass, that's only enough to build around 1 kilogram of hawk biomass. And 1 kilogram is 2.2 pounds. A lot of species of hawks might weigh 5 or 6 pounds. They seem like they should be a lot heavier, but they're really, not that massive. But 5 or 6 kilograms or 5 or 6 pounds is much more than 2.2 pounds. So that's not even one whole bird. Now you started with 1,000 kilograms of seeds, and you ended up with 2.2 pounds of hawk. You see how much energy is kind of given off as heat along the way, and how little energy is actually captured by the next step when it feeds on the step that came before it. All right, so if we take more of a chemical perspective, if we want to take glucose, like we talked about back in our previous chapters, and use that glucose to build, say, glycogen, that's going to cost some energy, right? Because we're taking a bunch, maybe 1,000 little individual glucose molecules, and we're hooking them up, we're forming some bonds, and we're forming one molecule of glycogen. We've taken 1,000 simple things, we've combined them into one complex thing. That's going to cost some energy. On the other hand, when we go to break down the glycogen, that's going to be more or less energy free, because anytime you convert from a more complex to a less complex state, you typically do not have to add very much energy, if any. All right, so going to more complex, you got to have some energy. Typically, the energy comes from ATP, which is being produced by the mitochondria in our cells. If you want to break down the complex things into simpler things, then that's going to give you a portion of your energy back. So you invest some energy building like glycogen, and you get some of the energy back when the glycogen is broken down. Right? Now, technically, you get all the energy back when you break down the glycogen, but because some of it's given off as heat, that's not biologically available, so that's why I say it's being lost. So this is kind of what we're dealing with here. If we take some glucose molecules, add some energy, we can make a more complex molecule of glycogen. If we then break glycogen down back into glucose, we get some of our energy back out again in the form of usable energy, and we get a lot of heat energy, which is, again, not available to living things to use also from that reaction. So that's a big part of what we're going to see in our next chapter when we deal with cellular respiration. Is we're going to take the glucose, we're going to take these guys at the bottom here, we're going to break them down, and we're going to use the energy from the breakdown of these guys to actually make some ATP, which can be used by the cell. All right, so we're skipping that slide. All right, now, the next big thing, and this slide, I think, is actually the most important slide in the entire chapter, okay? You really want to focus on the terms in this slide. Every single chemical reaction that occurs requires a little bit of a nudge to get started, a little bit of a push or spark to get going. Now, for some reactions, that's all it takes. You give them a little bit of spark, and the reaction just sort of happens, and it's done. Other reactions, you give them the spark, and then you have to keep adding more and more and more energy to make the reaction keep going. You got to keep adding energy to drive the reaction forward. But all reactions require at least a little bit of energy input at the beginning to get the ball rolling, so to speak. So that spark, or that little nudge of energy, is called activation energy. So the activation energy is how much energy it takes to get a reaction going in the first place. And really what's going on here with activation energy is you're getting the molecules of the reactants to move fast enough that they actually collide with each other and therefore react and form whatever products you're looking for. So you're actually trying to increase the odds of the reactants forming products by having a faster movement of those molecules. One of the reasons why this is important is because if you remember back to our chemistry chapters, what's on the outside of an atom but electrons. So if you've got a bunch of different atoms all having electrons on the outside, they're really not going to want to come into that close of a contact because those electrons all have negative charges and they're all repelling each other. So if you're going to get the atoms to actually collide with each other, they got to be moving pretty fast to make that happen. So another pair of really important terms, exergonic and endergonic. All right, so if a reaction is a net producer of energy, we say it is an exergonic reaction. If a reaction is a net consumer of energy, we say it's an endergonic reaction. Right? So exergonic gives off energy, exo is always out, and endergonic is going to consume energy because endo, or ender in this case, is always in. Right? So exergonic reactions always give off more energy than they take. Endergonic reactions consume more energy than they give off. Right? It's kind of the basic breakdown there. So the activation energy is particularly important when we're dealing with exergonic reactions because the rate of an exergonic reaction is inversely proportional to the amount of activation energy you need to get the reaction going. So in other words, if you have an exergonic reaction that requires a lot of energy input, when you get the reaction going, it's going to be pretty slow. But if you have a reaction that only requires a tiny little bit of energy input, then once you add that little bit of initial spark, the reaction goes very fast and it's done. Okay, so the rate of reaction is inversely proportional to the amount of activation energy you need to start the reaction. All right, so the more activation energy you need, the slower the reaction goes. So I'll give you a couple examples of that. Both very similar things. We're going to consider the amount of activation energy needed to burn a piece of paper versus the amount of activation energy to burn some gasoline, and then how fast those reactions go. And you kind of already see where I'm going with this, right? So if you want to burn a piece of paper, you get a lighter or a match and you put it next to the paper and it catches on fire and it burns. I wouldn't really call it really slow, but it's not a fast reaction because that oxidation of paper is going to require a fairly large input of activation energy. Now the gasoline, and if you've ever seen gasoline burning, like externally in the environment, and this is a public service announcement, don't do that because it's really super dangerous. It's a really fast reaction when you oxidize that gasoline. It's the same reaction, you're oxidizing it just like we did the paper, but because the gasoline has such a low activation energy for oxidation to occur, it goes really freaking fast once it starts. Paper, you need a lot more energy, so therefore it's a much slower reaction. Now, if we want to increase the rate of a reaction, then we basically have two options. We can either heat up the reaction, the reactants that are there. We can heat them up. That's going to make them move faster and therefore cause them to collide more commonly, more frequently, and that's going to cause the reaction to speed up. Unfortunately, in a living cell, if you heat it up too much, you kill it. So that's not really a very viable option to speed up reactions in a living cell. On the other hand, we can sometimes take advantage of this inverse relationship between activation energy and rate of reaction by lowering the activation energy you need to start the reaction, right? So if you take that exergonic reaction and somehow find a way to decrease the activation energy it needs, once you get it going, it's going to go faster. And if you decrease it even more, it's going to go even faster. All right, so this lowering of activation energy, this is what enzymes do. And we're going to talk a lot more about enzymes here coming up very soon in this chapter, but activation energy, because it affects the rate of reaction, we can lower the activation energy and therefore speed up the rate of reaction. All right, so this is a kind of an example of that, sort of a visual of how an enzyme actually affects the rate of a reaction. First thing I want to notice here, or want you to notice here, is that this is an exergonic reaction because the reactants here, what you start with, have more energy than the products that you end with. All right, so this energy was given off into the universe, into the environment, and the products have less energy than the initial reactants. That means it's an exergonic reaction. Now, without an enzyme present, without a catalyst present, this reaction needs a fairly large amount of activation energy to get going, and once it does, the reaction then goes to completion when it ends up with these low energy products. If you make this little bump or this little hill smaller by decreasing the activation energy, the reaction is going to go a lot faster. Now, notice how you don't actually get more product. It's not that having an enzyme or a catalyst makes you end with more grams of your product. You're going to end up with the same result as if you didn't have an enzyme. The difference is how fast you get that product. Right? So it's basically a race, right? So imagine you had a Ford Focus versus a Ferrari, right? You're going to drive these cars to the same finish line. It's not that the Ferrari has a closer finish line than the Ford Focus does. It's just that the Ferrari gets there a whole lot faster. It's kind of the same idea. If you don't have an enzyme, you're still going to get to the end point. It's just going to take longer. And if you do have an enzyme, you're going to get to that same end point, but it's going to happen a whole lot faster because the activation energy has been decreased. All right, so what catalysts do is they decrease the activation energy, thereby speeding up the rate of reaction. Now, we're still playing by the rules here. We haven't violated our laws of thermodynamics. We're not creating energy. We're not destroying energy. We're just lowering the amount that you need. Okay, so really by lowering the activation energy, we're still playing by the rules, like I said before. So we're not creating energy, we're not destroying energy, we're not converting things without having heat being given off. We're just kind of exploiting a loophole in the idea of an exergonic reaction going faster when it has a lower activation energy. This, like I said before, it's not that you get more product, it's not that you burn up more reactant, it's just that you do it in a shorter period of time. If you didn't have a catalyst, you'd still get the same amount of reactant turning into product, but it would just take quite a bit longer, sometimes millions of times longer without a catalyst versus with a catalyst. Right? Now, what we're going to end this section of lecture on is with something called the Gibbs free energy equation. And so what this is a way to kind of interrelate entropy and something called enthalpy, which we're going to talk about in a second. So the focus of the Gibbs free energy equation is this outcome, the letter G. G is the free energy of the reaction. So if you have a reaction that ends up giving you a positive G, that means energy has been given off and the energy can be used to do stuff. Now, on the other hand, if you have a negative delta G, that's a different story, as we're going to see here in a second. So the Gibbs free energy equation looks at free energy as a function of enthalpy, which I'll define for you here in a moment, temperature, and entropy. All right, so basically what we have here is enthalpy is the opposite of temperature and entropy. Right? These two terms, or this term and this pair of terms, these two guys are opposites of each other. The bigger this number is, the more positive this is, and the more that's going to be an endergonic reaction. The bigger this value is, the smaller this is going to be because we're subtracting this from this. The bigger this pair of terms is here, the smaller this will be, even to the point where G becomes negative. And if it's a negative G, that means then we're going to have an exergonic reaction with energy being given off, like I said a second ago. All right, so enthalpy is kind of the opposite of entropy. Enthalpy is a measure of energy in bonds. It is a complexity sort of a thing. And so if we have a reaction with a positive G, that's going to be an endergonic reaction. If we have a reaction with a negative G, that's going to be an exergonic reaction because energy is being given off from the reaction. All right. So like I said before, entropy and temperature are related directly, and they are kind of the opposite of our enthalpy term over here. All right. So what we can then look at is what's called delta G, the change in free energy over the course of time in a chemical reaction. If we have a positive delta G, that means that our products, our endpoints, have more energy than the reactants we started with. And of course, we're not creating energy. We're not allowed to do that. The first law says that we can't create energy. So the only way for the reaction to have, in a sense, gained energy over the course of that reaction is if energy was coming in from the environment. And therefore, any reaction where you have energy coming in is an endergonic reaction, right? Now, if we have a high enthalpy value, or if we have a low entropy value, we're assuming we're not changing temperature because, again, temperature changes will kill living things. So we don't really want to focus on changing that too much. But either having a lot of enthalpy or not very much entropy, both of those two things over the course of a reaction, building something up in complex or taking away chaos and disorder and randomness from the universe, both of those two things are going to end up giving you a positive delta G, and those things are indicative of an endergonic reaction. All right, so these reactions are, like I said before, not spontaneous, and they require not only activation energy, but continuous energy input after that initial spark of energy to get the reaction going. If we have a reaction with a negative delta G, that means then that the H value has gotten smaller and or the S term has gotten bigger, and we're not considering temperature change, so we're just looking at entropy and enthalpy. So if complexity is being lost and chaos and disorder and randomness are being increased, that would then give us a negative term over here, negative delta G, so the energy is being given off from the reaction, and that is, again, indicative of an exergonic reaction, which is spontaneous and occurs without much energy input beyond the initial spark of activation energy. All right, so there's kind of a lot to that, but once you break it down and understand it, it really kind of helps you get a better sense for what's really going on with an exergonic versus an endergonic reaction in terms of what's being built up versus what's being broken down. It really kind of helps you understand it more when you delve into what these parts of the equation mean. Now, I should have said this at the beginning. Don't panic. I'm not going to make you calculate anything. All right, but you do need to know what a negative delta G is and what a positive delta G is, what that means in terms of being, energy given off, energy consumed, exergonic, endergonic, those kinds of things. All right, so this is our endergonic reaction. We have some relatively low energy reactants. At the end of the reaction, we have some relatively high energy products. We know we're not creating energy, so therefore energy must be going into the reaction. And anytime we have energy going into a reaction, we know that's an endergonic reaction. On the other hand, if we start with high energy reactants and end up with low energy products, we know we can't destroy energy, so energy is being given off into the universe. And anytime we have a reaction with energy being given off into the universe, we know that's an exergonic reaction. All right, so we're going to end this section here. I'm going to pick up section 3 by doing a quick review of exergonic and endergonic reactions. And then in the third section, we're also going to start jumping into enzymes and talk about more of what they are and how they do it and those sorts of things. So we're going to cut this section off here, and we'll start up with the third section here in just a moment.